So I think Kasey's gonna launch a poll now. And the next section, we have 2 sections here left in this notebook. We only have time for one of them. So we're gonna take a poll, whether you wanna talk about noise, or if you wanna talk about earthquakes. You can go through the other one on your own time, or with the Slack channel afterwards. I'm sure people will kind of dig into both of them. But yeah, depending on what you want to talk about, this noise is kind of thinking about optical noise and seismic noise inside this well, and then the earthquake's kind of looking at aspects of actually interpreting the earthquake wave field.
It's neck and neck, Nate. I don't know, earthquake analysis is in the lead.
Oh, it's close.
Wow, this is a dead heat. Oh, yeah.
Ooh.
That's bizarre.
Every vote counts. This is important, guys.
Oh, noise analysis. You can mail in your vote. We'll read it next week.
You could be the deciding vote. All right, so it's getting...
Okay, moving left. People are maybe answering twice.
Okay, I'll end it at a minute. So 1, 2, all right. It's closed.
Okay.
Noise by 2. Oops, sorry, I'll share it.
Cool, so there we go. So noise it is. So please take a look at the earthquake afterwards. Stop that. Okay. So the noise of this well is pretty interesting, and maybe this is kind of a good. I'm glad people are, many people are interested in this. I thought it might have been only a few votes, so that's good. The noise is really important. I think it could be optical noise, could be seismic noise. So I've included. We were really just plotting in the last section this this first DAS file. So this was just a brief half second of a micro earthquake during an otherwise 15-second continuous recording, and we were plotting this file for the geophones. So if you run this next cell, we're going to be looking at a little bit longer of a recording, so 30 seconds on May 2nd, 2019. So that's represented in these 3 files and these 3 files of DAS data. So it just should take a couple seconds to finish reading. It doesn't actually download it. It just says it downloads it because of this workshop switch. We don't want to crash Utah's servers, so we have put it all here. Okay, so it's important to say that the earthquake data in the first couple of sections that we're looking at was pre-filtered. So it was filtered between 10 and 150 hertz. These data are not pre-filtered. So if you wanted to take a look at some of the noise in this kind of a record, from 0 at the wellhead to 1 kilometer deep, one of the things you could do is plot the spectra, right? So we can plot the spectra with this same, this utils function is going to plot either we can calculate amplitude spectra, or power spectral density. And the data, like we said, were recorded in strain rate. So that's a Silixa method outputs strain rate natively. So if we run this next cell, what we're doing is we're going to compute the power spectral density. So this utils spectra function takes PSD as a kind, so that's power spectral density, and then takes a trace number. So we're going to plot the 20th trace, the 220th trace, and the 1050th trace. And we're going to plot the spectra for those with these kind of clips in terms of the range that we're plotting here. So here are the traces, here are those 3 traces, and just to orient you along, the x-axis is frequency, y-axis is power spectral density relative to 1 strain per second squared per hertz. And so this is pretty interesting, right? Very different characters, just in 3 traces in this DAS array. And below, I'm showing the array image. So every column here now is a Fourier transform, or some estimate of the spectra. So we're actually looking at power spectral density. So it's not truly the Fourier transform, The PSD gives us a sense of the representation of different frequencies along the y-axis in this plot, from 1 hertz to 200 to 100 hertz and down to 10 seconds. Now, so you can look at these in either of two ways, right? So if you were to plot every trace, every column in this array of DAS data on this first plot, it would be way too confusing. But these traces are a good way to kind of represent a couple of different locations in your DAS array. So here I said I'm plotting the 20th trace. So the 20th trace, this one here is, if you actually look at the stats of this DAS trace, you'll see that it's at it has a distance of -180 in actual physical coordinates, where 0 is the wellhead. So this is back inside of the instrument room, actually inside of the interrogator at 180 minus 180. So you see a very high noise level there. And this trace, this green trace, is the bottom trace. So that's down at the bottom of the well. And it's actually in the well at, you're seeing this kind of lower noise floor. And right near that, just 2 gauges, 23 meters into the well, you have this kind of response in orange. So this kind of feature here is what that orange trace is seeing. So it's at 20 meters right here. And we can actually see this kind of larger surface waves, which are related to actually kind of machine vibration or operations at the surface on the well pad. So this kind of is pretty interesting. It decays to depth, but by 400 meters you don't really see it, see this noise, and we'll take a look at that in a second. At the kind of before the wellhead, you'll see this is really high power spectral density level. And then below about 1,000 meters, 1,000 meters, you're seeing kind of high levels also. But there's actually a few traces here, like this one and this one. I think you can see my cursor. Just make this a little bit bigger. So this trace and this trace are also kind of anonymously high. And you'll see a few other traces here, here, here. You see these kind of vertical lines. And those are potentially, one cause of that is actually photonic noise. So there's, this is an interferometry method. So if we think about this, the DAS is kind of a photonic instrument. We're measuring, the phase between two optical waves, and we can have constructive interference or destructive interference. And if we get a 0 in terms of the kind of destructive interference case, we can record kind of a faded trace, and so that's a photonic effect. I would kind of interpret these two traces in particular as being clearly photonically faded. There's another optical effect, which is kind of this noise here, which stripes across all the channels, and that's probably related to kind of an effect of maybe the fan or the kind of optical setup, some noise inside of the instrument that is overprinting on all channels, either before or after the digitization of the data. So let's plot this in a slightly different way. So that kind of gives us a sense of, this is a good, someone in a breakout group asked me what QA/QC meant. So I'll just say it's quality assurance, quality control is kind of a term. I think that this kind of step is a good quality control type of method, QA/QC type of method, to get a sense of what the noise is across the array in different locations, and also try and suss out what might be seismic noise versus optical noise versus the cable just being before the wellhead, kind of running along the surface or coiled in a room. Another way to plot that would be to compress everything along a different kind of axis here. So we can plot the noise level as a function of distance instead of as a function of frequency. So if we choose, so here I'm defining a function noise level. And if we just choose a range of frequencies, then let's say from 1 hertz and above, to kind of just to look at all the kind of the strain in a RMS sense or strain rate above a certain frequency, we can then plot this kind of a view. And this can be plotted either in strain rate or in strain units. So for the Silixa data, the data are coming in from the field in strain rate. And so we can plot them in this kind of noise level view, which is the native way that the data are recorded. Just a second, let's plot. Okay, so we see that the noise level is kind of at this level of minus 60 dB, minus 65 dB for this just brief 30 seconds of this file from 1 hertz up to the Nyquist. So the sampling rate for these data are 500 hertz. So the Nyquist to be about 250. So we're with this noise level function, we're plotting the RMS as a function of channel position along the array. And another way to plot this would be to integrate the data in time to get strain. So from strain rate to strain, and then plot the data in strain. And you'll see a kind of a difference here between strain rate and strain, the units. But I think this is helpful because you can actually see, those traces that were faded actually pop out. You can also see where you are in the well. It's much quieter versus up top and below, has this kind of optical noise or surface noise. And actually you can even see there's, this is a log scale, but you can actually see a slight increase with that surface noise inside the well in this kind of example. So here are those two photonic traces, photonically faded traces. Again, the below the section of the well and above the wellhead. So I think that this kind of noise level is a good way to also kind of QA/QC the data set or investigate the noise level. I would say that this is a good exercise to go through before we think about the earthquake. So I'm glad the votes kind of turned out this way, because this would be the background across which the earthquake would kind of be a signal above this noise floor for the well. And you might take a little bit longer of a time to kind of establish a really clean noise floor estimate. So not just 30 seconds, but maybe a few minutes of data. And there's other ways to kind of estimate this RMS, but we've just taken one approach here. And also we've only looked at 1 hertz and up, so we haven't looked at longer periods. So in terms of establishing a noise floor of the method, we'd maybe need to kind of reconfigure how we're doing this approach. But this gives you the basic outline for how you might think about noise levels in an experiment. So, right, let's keep going. So just another way, and again, this is kind of a whirlwind tour today of what we're looking at. So, so bear with us if you're not kind of able to follow along, perfectly. That's, totally fine. Even if I'm kind of moving too fast, the point is to put these tools out there, and everyone's going to move at a different pace here. So I just want to kind of get through this next section to show you the different views of how you can interpret DAS data. And kind of one of the other ways that's really neat to look at DAS data is not just in the frequency domain, but also in the wave number domain. And this is kind of, I'm glad we were able to kind of have this tutorial today to actually get to discuss kind of frequency wave number space, because it's the kind of I think when you have regularly spaced data in time, you're able to plot like a power spectral density like we've done above. But if we have regularly spaced channels, we can also plot the spatial frequency of a signal. So if you just run this cell, it's going to be calculating basically the Fourier transform in 2 dimensions. So FFT2 takes an array like what we've been plotting for the image of the DAS data set. It has a spatial axis and a time axis. So we can do a 2D Fourier transform and then calculate the frequencies and the wave number axes, and then plot it basically. And if you do that for a range of DAS data, you'll get this next image. And I've plotted, what I'm doing is I'm plotting the image first, and I'm defining some channel 0 to channel 1 across which I'm gonna do the 2D FFT to plot the frequency wave number axes. So we're only including from channel 198, which is near the wellhead, if you remember from the tap test kind of exercise, to channel 300, which is 300 or about 100 meters into the well. So here's the time distance axes of this plot. So again, just half a second, you can see there's that surface wave noise that I was talking about, the kind of vibration of everything at the surface. Optical noise, kind of horizontally striped, but we're just going to look at from this channel to this channel in this array. And here you're seeing the kind of frequency axis on the y, along the y coordinate, and the wave number axis along the x coordinate. And I'm, this is symmetric, right? Fourier transform is going to be symmetric along kind of across this space, but it's kind of I think it's a good convention to maybe plot only the positive frequencies, but then the negative and positive wave number axis, so that we can see that there's some the energy in this case is plotting over here, right? It's positive. This is again a log scale, so we have some 25 dB between the red and the dark blue here. And I'm plotting only between 15 and 25 hertz. Obviously this goes up to 250 hertz and down to 0 or very low frequency. Okay, so what is this white line here that appears to be kind of trending up from 0, 0 on this plot to this location? Well, that's for those of you who aren't so familiar with plotting things in frequency wave number space, this is going to be a velocity or phase, correctly phase speed at this position. So we have basically a 600 meters per second to 4,000 meters per second. Those are the dotted lines. And then 1.1 kilometers per second is going to be the center line of this plot. So this is going to show that the exact value of this is not too important, I would say, right now. I think the main point is that if you look at this seismic, the dominant energy between this channel and this channel is this kind of feature that's moving like this, right? You can see my cursor, hopefully. So this noise is that surface noise. And the point is that in this kind of a axis, we're actually plotting on this side of the wave number axis, right? So there's 0, and then we're plotting over here. So we're at positive frequency, positive wave number. And phase velocity is f over k. And so when we plot on this side of the frequency wave number axis, this quadrant, that suggests that the phase information, the kind of phase of this wave, is moving out causally in space and time. So it's moving from 0 space to in a positive spatial direction along this axis, and it's moving out in time in this direction. There would be, maybe in the earthquake case, things that are moving from the bottom of the well up. So they're moving out in time, but they're moving back towards the instrument. So those kind of earthquake waves as before, those would plot over here on this side of the diagram. And so this is this frequency wave number axis, plotting things in terms of a spatial frequency along the x-axis and temporal frequency along the y-axis, is a useful way to begin to think about different signals and how they propagate through the kind of DAS array here. So, right, so that's the noise section. I think we again break into, or just actually maybe take a break to talk for the next couple of minutes before we kind of move on. But there's questions down here at the bottom, which we could maybe handle separately.
I think we've got a couple of minutes now for any questions. Eileen, did you have ones already flagged?
Yeah, let me pull up that slide real fast for our last break.
Great.
Nate, is it okay if I take over screen sharing?
Yeah, let me just stop sharing. Thanks.
All right, so we're gonna go into our next break now. So we'll have until 3:30 Eastern. So one thing, we're gonna put this link into the chat. I think it was at the very top of the chat today, but we'll put it in again. But we've got a list of a lot of different publicly available DAS data sets that we'd like to encourage people to go and take a look at those. Also, if you know of any DAS data sets that are public that we don't have there yet, please post something in the like hashtag datasets channel on Slack, because we want to know about all of these. We want to be able to, have people's public data have an impact. So then we're going to come back and we're going to have a talk on cloud systems for DAS data distribution and other large-scale data distribution. So stick around for that. I'm really excited. We've got Nicole Taverna presenting that. And if you want to do some discussion during the break, head over to the Datasets channel, and you can discuss stuff like how you shared and accessed data among collaborators or publicly. As your data starts to get bigger, this gets to be a real challenge. And a lot of us working in DAS have run into this in many scenarios, not just hosting files on Google Drive or just with the GDR and the limitations in these systems. There's also a lot of efforts within IRIS to expand capabilities there. So go ahead and discuss your strategies for sharing large-scale data there. And we'll see you at 3:30. Thanks.